Welcome back. So we had a slightly unfortunate timing. I'm in the middle of a crash course, and we had a break for 2 weeks. So let me just remind you a little bit where we are now. So we are in this paragraph 2.3, which is basically entitled A Crash Course About Various Stuff. So we had a first part which was about homology, which is a part of algebraic topology. And what did we do there? Well, we said that if we have a graph that approximates well a surface, let's say a closed orientable surface of genus G, then you can define something which is called the first homology group of the surface, here with Z2 coefficients. And this vector space does not depend on the graph that is embedded. So this is always of dimension 2G. So it's a topological invariant. Moreover, this is endowed with a non-degenerate form given by the intersection. So if you take two cycles and you look at their intersection, this is something that is modulo 2. This is something that is really defined in homology. It only depends on the homology class of these cycles. And this form, I think I didn't say this, it's alternating. It's an alternating form. What does this mean? It means that if you take alpha, the form evaluated at alpha and the same alpha, this is always 0. So I wonder if you understand why this is true geometrically. So you have a cycle, and I claim that if you have this cycle and you look at the intersection of this cycle with itself, it's 0. So why is this true? So here you have to use the fact that the surface is orientable. So since the surface is orientable, if you have a cycle, its neighborhood is like a little cylinder. And so therefore you can push off this cycle a little bit aside. It's still the same homology class, but there is this joint. If you're not on an orientable surface, that's no longer true. If you're on the Möbius band, you take the cycle that generates the homology of the Möbius band. If you push it off, it actually intersects itself once. But here, this is since the surface is orientable. Okay. So this is a very rough summary of what I said about homology, which was already kind of a rough summary of the theory. And I had just started a part about quadratic forms. So here the setting is exactly the setting we have up there, but it's a purely algebraic setting here. So we fix H, which is a finite dimensional Z2 vector space. And a form which I want to denote exactly as above, but again, we're just in this algebraic setting. And this is a non-degenerate, oh, sorry, here I don't need this, an alternating form. Alternating bilinear form. Okay. And so I think I had already said last time, I had given you this definition. A quadratic form H endowed with this bilinear form is a map from H to Z2 such that, so again, it is not linear, but the defect of linearity is measured exactly by this bilinear form that we had fixed. Okay, and I think I just want to give you several facts, which will be in the homework. They're really not difficult. The first fact is the set, I'm going to denote it by Q, of quadratic forms on this is what is called an affine space over the dual H star of H. What does this mean? That is, or more precisely, the map given by this defines a freely transitive action of the vector space H star on Q. And again, what does this mean? i.e., Q is not empty, and for every fixed Q, for a fixed quadratic form, the map H star to Q is a bijection, is bijective. So these are many words, but okay, the real statement is this one. So it's, you always have quadratic forms, and moreover, this, each time you fix some quadratic form here, when you look at this map here, this is a bijection. This exactly means, the fact that it's surjective means that this action is transitive. The fact that it's bijective, it's freely transitive. Okay, these are just words, but you see, this is, you see the kind of thing. So if you take two quadratic forms and you add them, you don't have a quadratic form, right? So it's not a vector space. But when you take two quadratic forms and you add them, what you get is a linear form, actually. So the algebraic structure, this is called an affine space. Well, the way you have to think about it is a vector space that lost its origin, that's a saying. An affine space is a vector space that lost its origin. So you don't have an origin, but you can make differences. Okay. So this is very easy. It's an exercise. And the second fact that follows from it immediately is that if you make the following sum, this will be equal to 1 if alpha is 0 and 0 else. you see the first part, in particular, the first part implies that the number of quadratic forms is equal to the number of elements in H star that is in H. So all of this is exercise 1 of the homework of this week. And again, this is actually easy. The terminology is, if you're not used to it, can be a little bit heavy, but it's easy stuff. Okay, so now let's assume further that the form is non-degenerate. So let us assume that the form is non-degenerate. In this case, well, it turns out that the dimension of H is always even. It's also going to be part of an exercise. And if you make the following sum, so if you sum so this time you see I fixed Q, and I'm summing all these evaluations of -1 to the power evaluation of Q. This turns out to be plus or minus the square root of the number of elements in H. Hence we can define something which is called the Hopf invariant of a quadratic form. So definition. The Hopf invariant of a quadratic form as above is the modulo 2 integer Hopf of Q defined by the equation. So it's this basically the sign here, so it means I take 1 over square root order of H we know that this is plus minus 1, so I just say this is equal to -1 to the power Hopf invariant Q. It's called the Hopf invariant because it was devised by Kayit Hopf. He's a Turkish mathematician. And it used to be that on their bill, some value bill, you had the face of Hopf and you had a formula that we will not write, but another definition of the Hopf invariant was written on the bills in Turkish. I don't remember the name of the money, of the currency. Okay, so why is it called by his name? It's because he actually proved a theorem, so I'm going to put this as a fact. So that would be fact B3. So this one is our theorem. It's also not difficult. I'm not going to put it in an exercise because we're not going to use it, but it's not very difficult. It's that 2 quadratic forms are conjugate, and you can guess what I mean by this. So you have an isomorphism of the vector space that's okay. If and only if they have same Hopf invariant. Okay. That's also going to be proved in exercise. It's also called the Democratic Invariant. Because actually, if you look at, well, you're going to see in exercise, if you look at it, actually, since the form is non-degenerate, a quadratic form Q like this will always take a certain number of times the value 0, certain number of times the value 1, and there's never going to be a tie. It's always going to be one of them. It's going to be more often taken. And the Affine invariant can be defined as the value which is taken the most often, therefore democratic invariant. So you could just define it, Affine invariant, saying, okay, the quadratic form, it never takes the same amount of time, 0 and 1. It takes more often one value. This is the Affine invariant. That's another way to say it. You will see. Okay. There's an equation now that we will use. It's going to be fundamental for our theorem. So I'm just going to put it like this. But of course, now it's a little bit, it comes in an unexplained way. So for any alpha in H, we have the following equation. Again, you just have to have some patience. Next week, you're gonna see that it's gonna be the formula that's gonna give us the precise form of the partition function for the Dimer model on a general surface. Just believe me. So this is also an exercise. And then the last algebraic fact that I'm gonna need is that so remember, the dimension of H is even, so let's say that it's 2G for some natural number G. Then there are exactly 2 to the power G minus 1, G plus 1 quadratic forms with Affine invariant 0. So they're called even, that's the even ones, even quadratic forms. And 2 to the power G minus 1 to G minus 1 quadratic forms with Affine invariant 1, and these ones are called odd quadratic forms. Let me just check. I think that's correct. Yeah. Okay. So all of this, basically except our theorem, all of this is exercise 2, homework 6. So I don't claim that you need to understand perfectly this kind of stuff to understand the Dimer model on homogeneous surfaces, but if you do the exercise, you're going to have basically a almost complete proof of the general Pfaffian formula. Okay, maybe just as an example, if G equals 1, then we have 3 even, then we have 3 even quadratic forms and 1 odd. Okay. Okay, that's all I needed about quadratic forms. And now I'm going to pass to the third and last part of this crash course, This is about spin structures. And this is really geometry. So unfortunately, I mean, the precise formal definition of a spin structure is a little bit complicated in the sense that it uses, it's defined in terms of cohomology, of principal bundle, and it's terminology. It's not very complicated objects, but the concise way to present them is I find too complicated. So therefore, I'm not going to give you a precise definition, but I'm going to give you an idea, a flavor of what these objects are. So we shall only give a flavor, an idea of what these objects are. But as it turns out, spin structures on surfaces, they're very easy to understand because actually they're given by quadratic forms on the homology. So that's going to be the punchline. But let's say intuitively, a spin structure, let's say on a surface, is a way to count modulo 2 winding number framed closed curves. A framed curve, I mean a curve that is endowed with a vector field. A closed curve okay. So I'm going to put a definition in quotation marks because again, it's not a precise definition at all. But let's just say that this is the kind of object we want to have in mind. A spin structure so we're going to work on an orientable surface sigma is a map, let's write it lambda. So from the set of framed closed curve on sigma to Z2 such that I want to state two conditions. So again, we are measuring we want to measure winding numbers of curves with tangent vector fields. So for sure, I want that if I have a small disk on the surface, and this is the boundary of the disk, so let's say that here, that's a small disk on the surface. This is my curve lambda, and it's endowed with a vector field that is like that. This, obviously, I would like this to count as a 1. Okay? This is something that turns once. I think that's kind of clear. And on the other hand, if I take, same thing, a small disk, I look at its boundary, but along the boundary, the vector field is constant. this should count as 0. So the question is, how can you give yourself a spin structure? How can you encode such a thing? So then there is a way. It's via vector fields. So one can obtain spin structures via vector fields on the surface. How? So not any vector field, so let me give a terminology. So let X be a vector field on sigma with isolated zeros. So you have your surface and you have a vector field on the surface, and ideally what you would like is to have no zero at all. But as you may know, and this is an exercise also, the only closed orientable surface on which you can have a vector field with no zero at all, do you know which one it is? It's the torus. It's only on the torus. And this is an exercise. But so it means, okay, now we don't want to deal just with the torus, we want to deal with all the surfaces, so it means you have to allow some zeros, but actually we're going to want zeros that are kind of special, of so-called even index. So now I would like to define what is an index of a zero of a vector field. So the index of x at small x in sigma is, so let's denote it this way. So it's an integer. The integer given by the winding number of, so let's make just a small picture. So I have x, and I look at a small disk centered at x. I look at the boundary of this disk. Let's say I call it gamma x. And I want to look at the winding number of x along gamma x with respect to the constant vector field. So let me just explain this a little bit further. So you see, I have this x, and I have a small disk around it, and since it's a small disk, it makes sense to consider a constant vector field along this disk. So here I can very well just say, okay, I point in one direction. Okay. So I fix this one direction. And then I'm not going to draw on top of that the other vector field x, but you see, if at any point, maybe I will do it. So at any given point, let's say here, I have another vector field x. And what I can do, I can go around the circle, and I can just count how much does this vector field x turn with respect to the fixed vector field I have. Okay, this makes sense. This is an integer. Okay? And this is called the index of the vector field at this point. So maybe let me just give you a couple of examples.
Is x 0?
Sorry?
Is x 0 with any x?
X can be anything, but that's the first example. If x is not a 0 of big X, then the index is 0. Right? In this case, you see you have your vector field X. I don't know, let's just draw some kind of vector field that is not 0. And I pick a point, small x, that is not a 0. And okay, you see, you just look at a small enough disk around it, and the vector field big X will be locally like a constant vector field, so it will not turn with respect to the constant one. So this has no interest if you're not at a 0. Okay. If X is a source, then let's try to compute the index. So that is, I'm going to have something like that. I have X, which is here in the middle, and I look at a small disk, and you see you just go around this disk, and you see that this vector field here, it turns once here in the trigonometric direction with respect to a constant vector field. So here the index is +1. Okay? If you look at the sink, it's the same, it's +1. Then you can have well, anyway, you can have various configurations. Okay. So why am I talking about this now? So I'm going to give you some facts.
You said async is also +1?
I'm sorry?
You said async is also...
Async is also +1. Let's try. You fix your point here, you're pointing in this direction, and you're also going like this, right? Okay. Facts. So now I'm in this list. C facts. Okay, so first a fact about spin structures. So the set of spin structures on sigma is an affine space over the dual of the homology. So in particular, the number of spin structures on a given surface is given by the number of elements in H1, that is 2 to the power 2g. Since I did not define in a proper way what spin structure is, there is no way you can prove this, but okay. Second fact, which is the so-called Poincare Hopf theorem, which you might have heard of, states that if you have, okay, I'm not going to repeat what X is, if you have X a vector field with isolated zeros, if you sum over all the indexes, let's say over all the points, you will get the Euler characteristic of the surface. Yeah. So again, here I'm summing over all points in the surface, but really what I'm doing is summing over all the zeros, right, of the vector field. This is a very nice theorem. And of course, now you see why, what I had said before, right? The only closed surface with no zeros, the only closed surface where there exists a vector field with no zeros must have Euler characteristic 0, right? And then a third fact that explains why I had started talking now about vector fields is that if you give yourself a vector field with only zeros of even index, then this gives you, for free, automatically a spin structure. How does this work? So let X be a vector field on sigma with isolated zeros of even index. Is this always possible? Yes, it's always possible because of this theorem. So you see, this theorem, the Euler characteristic is always even. So it means that at least there is no obstruction to having a vector field with zeros of even index only. And it's a fact that you can always, if you have a surface, orientable closed surface, you can always find vector field with isolated zeros of even index only. The way to do it is you take any vector field with isolated zeros, and if you have two that are of even index, you just kind of concatenate them together, and these indexes will sum up, and and since the sum of all indexes is even, you can do this. You can pair. There's an even number of zeros of odd index, and you can pair them up like this. Anyway, you can have a vector field with isolated zeros of even index, and this induces a spin structure, lambda x, as follows. So remember, we fix gamma a closed curve, closed frame curve, framed curve. Then you define lambda x of gamma as, what do you do? Well, you do the obvious thing. Now what do you have? You have a curve gamma which is framed. So it has some framing. I don't know how it looks. And on top of that, you have some vector field, some fixed vector field x. And what you do, you simply say that this is the winding number of x along gamma with respect to the framing of gamma. Again, you have a curve that is closed. You have two vector fields on this curve, so you can count how much one is winding with respect to the other, simply. Okay. And I just erased here, but the fact that, remember, we wanted that lambda x of this thing here. We wanted that this should be 0, right? That was the second condition. And you recognize that this is exactly the condition that the index is even. Okay. That whenever you have a 0, it's of even index. And I'm just going to state here, and all spin structures are of this form. So you know when you follow a class or a talk, or sometimes the speaker goes really far astray, and you really wonder, why is he going so far away? So I think now this is the worst time in the whole class with respect to this. So now I really wander very, very far away. So now I'm going to start coming back, okay? So first of all, the first part is I'm going to explain why spin structures and quadratic form are the same thing on the surface. So already it's going to be, oh, okay, so at least these two things, they're the same. And then I'm going to explain, and then we're going to go back to graphs on surfaces. Then there's going to be dimers coming back, and then Cassadine orientations, and then we're going to have a proof that is like 5 lines of the general Affine formula. But now, of course, it's a little bit, it's kind of a difficult time. Let's see. Okay, so I will state the main theorem of this part now. Maybe I'm just going to go 3 minutes overboard, but I think it's better not to leave you just here. Okay, so the main statement of this section is the following one. Is the following theorem of Denis Johnson. So so we consider a spin structure which is given by a vector field like this. X with zeros of even index. Okay. Now we fix a curve, smooth, oriented, closed curve on sigma, and we don't want it to pass through the zeros of x. And I'm going to denote winding x gamma denote the winding number of the velocity vector field of gamma with respect to x. So again, use the same thing. So you have some vector field, some ambient vector field, which has some zeros. Then you have a curve gamma on it, and you want to look at the velocity vector field. So that's what I'm drawing right now, etc. And you want to count how this velocity vector field turns, how many times it turns with respect to the fixed vector field x. Okay, theorem. Maybe I'm going to state it on the other board. Again, it's due to Johnson in 1980, and it is not a hard theorem, but we're not going to prove it. So, given a homology class here, represent it by a disjoint union of simple closed curves let's say gamma j. Let's say avoiding the zeros, okay. Okay. Then the equation, the following equation, Q lambda of alpha equal sum over J winding number, how did I write this? X gamma J plus 1 modulo 2 gives a well-defined quadratic form Q lambda on the homology of the surface. Okay, let me just already pause for a while. So on and maybe what I'm going to do is already make, so the statement is not finished, but I'm just going to make already a kind of a example or remark then. So let's just take the stupidest example of sigma being the plane, or the sphere of the plane. So example, let sigma equal the sphere or the plane, and X be the constant vector field. What does this statement say? So, in this case, of course, there is only one homology class. There is no homology in the sphere in the plane, so it means that you just have this zero. So, and this class can be represented by a simple closed curve, any simple closed curve. So this statement says, well, if this is a quadratic form on 0, it means that this number should be 0. It means that this should always be 0. It means if you have a simple closed curve in the plane, its winding number is always odd, which is kind of clear, right? If you have a simple closed curve, the winding number of its velocity vector field is always odd. Actually, it's always plus or minus 1. That's a theorem of Hopf. But, okay. So in the plane, it's just the stupid statements that, so this means that if gamma is a simple closed curve, then its winding number is always even. And of course, winding number measured with respect to the constant vector field. Sorry, is always odd. So you have to think as spin structure as kind of a generalization of this. So in the plane, you ask yourself, okay, how can I measure winding numbers? Well, there is an obvious sensible way to do so. You just fix the constant vector field and you measure how your curve is turning with respect to this constant vector field. If you're on a surface, how can you measure this? Well, there are many ways to measure this, and these different ways are called spin structures, and that's what we're looking at right now. So the general statement is this. Moreover, the map which to lambda associates Q lambda is an H1 sigma Z2 equivariant bijection between S, the spin structures, and the quadratic forms on the surface, which I want to denote like this. So it's a bijection, and it's both of these sets have an action of this space here, and this bijection is coherent with this action. So it just means, actually, so the bottom line of all of this is spin structures on surfaces, they're simply given by quadratic forms on the homology with respect to the intersection form. That's it. And again, we are not going to prove this theorem, but it's easy. Okay, it's not a complicated theorem. Okay, and I will just give you one more example because now everything is kind of fresh. And then I will stop. Then it's going to be the end of the crash course part. So let's say that was the first example. So in this case, of course, the set of spin structures is given by a single element, which we can describe as the spin structure corresponding to this constant vector field. And of course, you have a single quadratic form, and it's the zero quadratic form. Okay, there's not much. And I want to give you a second example. So let sigma be the torus, and let X be the constant vector field. Again, it's possible in the torus. So if you picture the torus as a square, you just have this constant vector field in one direction. And you can even picture it on the actual wrapped up torus, saying, okay, you always go in one direction like this, for example. Okay, and now I want to try to understand a quadratic form, the quadratic form corresponding to this vector field. Okay, so let alpha beta be a basis of the homology, and I'm going to draw it. I'm going to draw like. See that this is alpha, this is beta. Okay, actually what I drew was representatives of the homology class given a basis. And let's try to compute these winding numbers. So then the winding number of do you see what we get here? So if you go along beta and you look at the velocity vector field, well, actually beta is always pointing in the same direction. You're not moving, so this is 0. And here, if you look at alpha, it's actually also constant with respect to the vector field. So this is actually 0. Okay. So this means that the corresponding Q lambda is Q lambda of alpha is 1, and it's the same as Q lambda of beta. So for lambda equal lambda x, we have this. So it means, so of course we also have that Q lambda of 0 is equal to 0. This is always the case. And then with this we can compute the last value, alpha plus beta. This is q lambda of alpha plus q lambda of beta plus the intersection of both, which is 1. So we get 1 plus 1 plus 1. This is 1. So now I can actually compute the Hopf invariant of this quadratic form. So we get that minus 1 to the power of the Hopf invariant of q lambda is 1 over square root of 4 times the sum of all these values. So minus 1 to the power 0, and then the three others that give minus 1. So we have plus 1, minus 1, minus 1, minus 1. So this is minus 2 over 2, so this is minus 1. So we see that the Hopf invariant of q lambda is 1. So it means that if you look at the constant vector field, the associated spin structure is an odd spin structure. So this is the odd spin structure on the torus. And remember, I had given as an example that in the case g equal 1 is the torus, you have one odd spin structure and three even ones. And so the three others are even. And okay, I hope this example explains a little bit better what's going on. Maybe the last thing, so here you might wonder, okay, then how do I give myself the other spin structures, right? So here, the constant vector field gives you, well, actually a natural way to do it is you just, so let's say that this is alpha, and you just go around, you don't change it except at the neighborhood of alpha, but at this neighborhood of alpha you make a full twist of the vector field. So that each time you cross it, you're actually making a twist. This will change this into 0, and that gives you another spin structure. And if you want to have another one, you do it along beta, and if you want the last one, you do it along alpha and beta, and you have the 4 different spin structures. Okay. Okay, let's make a 15-minute break. Now we're at the end of the crash course, and believe me, in 5 minutes after the break, you're going to have Cassadine annotations coming, well, Dimer configurations and then Cassadine annotations, and it's going to all come up together. Okay, 15 minutes. Good. So that was the end of the crash course part, kind of hardcore. And now, the general fucking formula. Okay, so I will not have time today to prove the formula, but it's going to be like 15 minutes in next week's class. We're going to be done. For now, we're still going to be kind of playing a game where we pretend we're not talking about the Dimer model. But so let's play this game. We have let G be a finite graph embedded in a surface, in an orientable closed surface. Sigma. Okay. And of course, I want such that the complement of G is made of topological disks. Consists of topological disks. Right, so this is always possible. If you have a graph, you can always embed it in a surface in this way. Now, the goal will be, we would like to try to encode combinatorially a spin structure on the by a data on the graph in the surface. So encode a spin structure, or equivalently, well, a vector field with zeros of even index. We want to encode this by some combinatorial data on the graph. On the graph. So let's see. How can we do it? So we have our graph that is embedded on the surface, and so what we will do, and we want to construct a vector field on the surface. So what we will do is we will move up the dimension of the cell complex that we have. So the 0 dimension are the vertices of the graph. So first I will construct a vector field along the vertices of the graph, then I will extend it to the edges, and then I will extend it to the faces. How can I give myself a vector field on along the vertices? So I need to point to give myself one direction at each vertex. How can I do this? Well, let's say that I fix a Dimer configuration on the graph. It means that at each vertex I have a given direction, the direction of the Dimer, right? So let's say I fix a matching, a perfect matching of the graph, and of course this defines for me a vector field, let's say unit length vector fields, along the vertices. At each vertex you point in the direction of the adjacent Dimer. There is a unique one. So at this vertex you will point here, at this vertex you will point there. Okay? So to define, so it's a vector field x, to define x along the vertices of the graph, fix a perfect matching M on the graph, and define x by pointing in the direction of the adjacent Dimer. Okay? This is not very visible, but I think it's clear. Each time you have a vertex, you have an adjacent Dimer, a unique one, and you just point in this direction. Okay, now we want to extend this along edges. So let's again make a little picture here. Let's say that we have a Dimer here, for example, a Dimer there. So we already know that we are pointing in this direction here, pointing in that direction there. And now I want to extend it along the edge. Do you agree with me that basically there are two different ways to extend it? There is a natural way by going like this, natural way by going like that. Okay? Two ways. Well, on an edge, there are also two orientations. So what I'm going to do, I'm going to fix a convention. I'm going to say, okay, I'm going to fix an orientation on the edges, and I will fix a convention on whenever I point in this direction, it means that I'm extending the vector field in some way. Okay? So there are two natural ways. There are more than that because I could twist n times, but the most natural ways, there are two natural ways to extend x along each edge. Let us encode this by an orientation. I will call this orientation omega on the edge of the graph. And I will use the following convention. So let's say that the orientation here is like this. And I'm going to draw, maybe on another picture here, I will draw my vector field. So we know that here it's like that. Here it's like this. So what I will do, it might seem a little bit complicated, but there are some subtleties that, well, make it necessary, I believe, to construct it this way. So what I will do is first, I start at the beginning of the orientation and I move like that. First, I will turn counterclockwise until I face in the direction of the edge. So first part, I go like this. Okay, so that's the first part. I turn counterclockwise until I face the direction of the edge. Second part, I will turn counterclockwise, I will turn clockwise until I face in the other direction. So this means I do like this. Okay. So this now is the other rotation. And finally, I turn again counterclockwise until I reach the final direction.
It doesn't work to just go clockwise.
So the problem is that then it's a little bit difficult to say it's well defined. So you see, imagine that you have your two dimers sticking out like this. And you move your dimer a little bit like that, then it's not stable. Your definition is not stable. So if you have your two dimers like this, and you're slightly a little bit more like this, in this one it means it almost doesn't turn. But then if you're like this, then it makes a full turn. And so therefore you run into problems. This is why you need to make this kind of a little bit more complicated definition to have everything working. Okay, so now we have used a perfect matching to define the vector field along the vertices. We used an orientation, arbitrary orientation, to extend it along the edges. And of course now, since the faces are topological disks, when you have a topological disk and a vector field, non-vanishing vector field along the boundary, well, you can just extend it to a vector field along the whole face with a zero in the middle. Okay, that's a cone construction. Right? So you imagine you have your face that is like a disk, and you have your vector field that is making these crazy things along the boundary, and you just extend it by making it smaller and smaller until it's zero in the middle. That's called a cone construction. So since each face is a topological disk, one can extend. Okay, we can extend it to a vector field x, which will really depend on omega and on m, on the whole surface with a zero that I will call x of f in the middle, or inside each face f of G in sigma. Now here is the nice lemma. So we have constructed a vector field with isolated zeros. But of course, what we really want is a vector field with zeros of even index. So we would like to know when the zero inside a face is of even index. And here's the answer. The index of x omega m at the face f has the same parity as n omega boundary of f plus 1, where you remember n omega of boundary of f is, so you have your face, it's oriented, so you can go around the face and you count the number of times that omega is facing you, right? Number of times that omega does not correspond to the orientation of boundary of f. Do you understand what this means? This means that the vector field that we have constructed has zeros of even index, that is, defines a spin structure, if and only if this is always odd for every face. And this is the exactly Cassadine condition, right? So we see Cassadine condition appearing like this. So maybe I will prove the lemma, I will at least give an idea of the proof, but as a consequence, omega defines vector fields with zeros of even index, and this is something that we want, because then we have Johnson's theorem, if and only if n omega boundary of f is odd for each f, which is precisely Cassadine condition. So let me give a proof of the lemma. So you just have to notice, to observe, it's not difficult, that if you change omega along one edge, the right-hand side will change parity, this is clear, this is really by definition, and the left-hand side as well. So here you just have to notice that if you change this omega, if you change it, then when you count the winding number that defines your index, then it changes by plus or minus 1. Okay. Observe that if one changes omega on one edge, then both sides change. And the sides, I mean modulo 2, right? Again, the right-hand side, it's by definition. The left-hand side, it's, well, there you see that you need this kind of difficult convention, but you can check that it works. Okay, so it means that what I can do, I can switch all the orientations so that I'm always going around the face in the counterclockwise direction, so meaning that n omega is equal to 0. So hence, we can assume that omega is coherent, agrees with boundary of f everywhere. So the orientation on boundary of f everywhere. So n omega boundary of f is equal to 0. So it means I have something like that. But then in this case, so now let's try to compute this index. I have to compute the winding number of my vector field along the boundary of the face with respect to a fixed direction. But here, if you look at it, let's assume that, so if we go along the face like that, and we're always doing this. So here you can see that whatever the Dimer configuration is, you're always pointing outside. See, you're pointing outside, pointing outside. You will always point outside. And therefore, your vector field is actually homotopic to a source, and the index is 0. Okay. In this case, observe that x omega m is always, well, is homotopic, meaning you can deform it continuously to a source. What I mean is it's homotopic to something that always goes like this. And in this case, of course, the index is +1, so it works. So index okay? That's nice. Now we're starting to come back to what we know and love, Dimer configurations and Cassadine orientations. So let me just give you some terminology. Now it makes sense to talk about the following things. So let's say that an orientation omega on G embedded in the surface is a Cassadine orientation. Right? We had defined it for a plane, but it makes sense to define it for on any surface if n omega f is odd for any f. And I also want to say that two Cassadine orientations are equivalent if we have something. So two Cassadine orientations omega, omega prime are called equivalent if they are related by the following moves. By a sequence of the following moves. And I will simply make an example. And I just want to keep this because I might need it. I'm not completely sure. So the move I'm talking about, so let me make an example. Okay, so let's find a Cassadine orientation here. Okay. This works, I think. Yes. So let's say that this is omega. And the move that I want to consider is you pick a vertex. Let's say I pick this one. And I invert the orientation of each edge that is adjacent to this vertex. This is equivalent to omega prime, which is the same thing except that I have inverted all the orientations that were adjacent to the vertex. So you agree that if you have started with a Cassadine orientation and you make this switch, then what you get is also a Cassadine orientation, right? Because each time you go around the face, you will have changed 2 orientations, so the parity does not change. Okay? Right. But now, let's look at this example. So, okay, So let's look at this example. Is this really a Cassadine orientation? Remember, now we're no longer in the plane. We want to look at closed surfaces. So here, really, I still have one face to check, right? The outer face, right? So here, if I go around this face, I agree, disagree. It's odd. It's fine. If I go around this face, agree, disagree, odd. It's fine. But I still need to check the outer face. Let's check the outer face. Need to go in this direction. Disagree, 1, disagree, 2, disagree, 3, disagree, 4, disagree, 5, agree. 5, that's odd, it works. But it does seem here that I might have gotten lucky because I had checked these 2 here, and it turns out that the outer face then automatically works, right? Well, at least it looks this way, and it is actually the case. But here one might wonder, actually, do you always have a Cassadine orientation on a graph? So question. Remember, in the plane it worked because we didn't care about the outer face. But we had constructed a Cassadine orientation with, you remember, this dual graph, but we never checked that at the outer face it actually worked as well. So question, does any graph embedded in a surface admit a Cassadine orientation? The answer is no. Example. Let's take a stupid example of this graph embedded in the plane. Okay? So I'm going to give you a Cassadine orientation for the face inside. Oops, no. Okay, agree, disagree, it's fine. Let's go outside. Agree, disagree, 2, that's even, doesn't work. And you can just check it doesn't work. What is the problem with this graph? Why did it work with this graph? Anybody can guess? So that's a proposition.
There are a number of edges on the face, the outer face?
No. It is a question of parity, but it's not a question of number of edges, it's a question of number of vertices. So proposition, a graph in a surface admits a Cassadine orientation if and only if it has an even number of vertices. And this is really nice, first, because it does not depend on the way you embed your graph. Second, because of course we look at dimers, so we better have an even number of vertices, so it means we're safe for the rest. So proposition, a graph G in sigma admits a Cassadine orientation if and only if this is even. Furthermore, in this case, the set, I'm going to introduce a notation, some kind of script K of G in sigma, the set of equivalence classes of Cassadine orientations is an affine space over H upper 1 of Z2. Exactly like these other, like the spin structures and the quadratic forms. So what I will do, I'm simply going to give the proof of the first part of the proposition. Then probably I'm going to stop. It's a very nice argument, an Euler characteristic argument. Proof. Okay, so let omega be any orientation, an arbitrary orientation on the edges of G and sigma, and define C omega. It's a map from the set of faces of G and sigma to Z2, defined by C omega of F is N omega boundary of F plus 1 modulo 2. That's just the definition, but note that omega is a Castellan orientation if and only if this thing is identically 0, right? If and only if C omega is everywhere 0. Now, let's compute the following quantity. We compute the sum over all faces. I'm going to write it like this for the faces of C omega of F. By definition, so this is plus 1, so we have that the number of faces plus sum over all faces of N omega boundary of F. Do you understand what this is? So you're summing over all the faces and you're counting. Here you have exactly the number of edges. Each edge will be counted exactly once. To be counted once, it's going to be counted when we count the face, the one face that is adjacent, whose orientation corresponds to not the orientation of this edge. So this actually is equal to the number of edges. So what we get is number of faces plus number of edges. But now remember that the Euler characteristic of a surface is even, so this has the same parity as the number of vertices. So since the Euler characteristic of a surface, which can be computed as number of vertices minus number of edges plus number of faces of our graph, because we have chosen the graph to approximate well the surface, this is always even. This is 2 minus 2g. It's even. So what do we have? We have that this sum here has the same parity as the number of vertices. And now we're basically done. So I want to show that there is a Castellan orientation if and only if the number of vertices is even. Well, so let us assume that, so if omega is Castellan, then it means that C omega is always 0. It means that when we do this sum with this omega, we get 0. That shows one direction. Let's show the other direction. Conversely, if V is even, then you start with any omega, we have that this sum is even. It means you have an even number of faces where it doesn't work. Now you see what you can do. If you have an even number of faces where it doesn't work, you just pair them up. Then, hence, we have an even number of f such that C omega of f is odd. Then what do? You pair them up. Say I have one of these faces here, another face here. And what you will do is you will consider a path that joins these two faces that is transverse to the graph. And you will inverse the orientation omega along every edge that intersects this path. And you see that each of the faces you will cross twice, so you will not change anything, except this first face here and this last face here, which we have crossed only once, and therefore you change the parity of C omega on these two faces. You have an even number of these faces, so you can pair them up like that, and then you're done. So let me write this. Pair them up and invert omega along each edge intersecting the path gamma as illustrated opposite. The resulting omega satisfies C omega equals 0, i.e. is Castelline. And this is not the end of the proof of the proposition, but it's the end of the proof of the first part. So I'm going to stop here. So since I'm already over time, I'm not going to ask you if you have questions now, but I'm going to stay in the room because I know that I went a little bit fast. And so if you have questions, you can ask me. Otherwise, let me just tell you that next time we're going to have the reward of these difficult times, because we're going to have this formula, general Affine formula, that will come in a matter of maybe 15 minutes after the beginning of the class next time. Have a nice week. See you next week.